Welcome to NEF Center. This presentation we will talk about relative kinematics. The main idea is that motion is not always absolute. What we observe as motion depends on the reference frame from which we observe it. In this presentation, we will develop a visual understanding of kinematics and relative reference frames. On the right side, we can see two coordinate systems. The first one, labeled R, represents a fixed reference frame, while the second one, labeled R', represents another reference frame whose axes may have a different position or orientation. The dashed curves illustrate how the two coordinate systems can be related through translations and rotations. The central question throughout this presentation is simple. How does the description of motion change when we change the observer or the reference frame? This is the fundamental idea behind relative kinematics. Now let us consider a simple physical situation. Imagine a bus moving along a road with two observers. Observer A is standing on the road, while observer B is inside the moving bus. Consider the position of a target, labeled M. From the point of view of observer A, the target may appear to be moving because the bus itself is moving relative to the road. However, from the point of view of observer B, the same target may appear to be at rest, or it may have a completely different motion. This illustrates a fundamental principle of mechanics. The state of motion or rest is relative to the observer. In other words, there is no meaningful statement such as, "this object is moving," without specifying the reference frame. Therefore, before describing position, velocity, or acceleration, we must first identify the reference frame being used. To describe motion mathematically, we need to establish the geometry of our reference frames. Here we have two coordinate systems. The first system is R, with origin O and axes X, Y, and Z. This represents the absolute, or fixed, reference frame. The second system is R', with origin O' and axes X', Y', and Z'. This represents a moving reference frame. The position of point M can therefore be described in two different ways. In the fixed frame, its position is represented by the vector OM. In the moving frame, its position relative to O' is represented by O'M. We can also describe the position of the moving origin O' relative to O. Therefore, the geometry naturally separates the motion into two parts: the motion of the reference frame itself, and the motion of the object relative to that frame. This geometric decomposition is the foundation for the velocity and acceleration composition laws that follow. We now need to distinguish carefully between three different types of motion. The first is absolute motion. In this case, we use the fixed reference frame R, and we describe the motion of M relative to R physically. This corresponds to observing a passenger from the road. The second is relative motion. Here, we use the moving reference frame R', and we describe the motion of M relative to R'. This corresponds to observing the passenger from inside the bus. The third is entrainment motion, sometimes called the motion carried by the moving reference frame. This describes the motion of the moving frame R' itself relative to the fixed frame R. So we have three different questions. What is the motion of M relative to R? What is the motion of M relative to R'? And what is the motion of R' relative to R? Keeping these three motions separate is essential for understanding relative kinematics. We can now establish the fundamental composition law for velocity. The absolute velocity of point M, denoted by V sub A, is equal to the sum of two contributions, V sub A equals V sub R plus V sub E. Here, V sub R is the relative velocity of M as measured in the moving frame R'. The term V sub E is the entrainment velocity, which represents the velocity produced by the motion of the reference frame R' relative to R. The vector diagram at the bottom illustrates this addition geometrically. The relative velocity and entrainment velocity combine to produce the absolute velocity. Therefore, velocity is additive across reference frames. The key rule to remember is, absolute velocity equals relative velocity plus entrainment velocity. This equation is one of the central results of relative kinematics. The entrainment velocity requires a more detailed examination because it can contain both translation and rotation. The first contribution is translation. If the moving reference frame R' simply translates without rotating, every point attached to the frame has the same translational velocity. In this case, the entrainment velocity is determined by the velocity of the moving origin O'. The second contribution is rotation. If the frame rotates with angular velocity omega, a point M located away from the rotation axis acquires an additional velocity. This rotational contribution is represented by the cross product omega cross O'. Therefore, the complete entrainment velocity is v sub e equals v sub o prime plus omega cross o prime m. The first term represents the translational motion of the origin, while the second represents the rotational motion of the reference frame. An important special case occurs when the frame undergoes pure translation. In that case, omega equals 0, and the rotational contribution disappears. Velocity composition is relatively simple, but acceleration composition is more complicated. The absolute acceleration is written as gamma sub r equals gamma sub r plus gamma sub e plus gamma sub c. The first term, gamma sub r, is the relative acceleration measured in the moving reference frame. The second term, gamma sub e, is the entrainment acceleration produced by the translational and rotational motion of the reference frame. The third term, gamma sub c, is the Coriolis acceleration. This is the important difference between velocity and acceleration composition. Velocity requires two main contributions, while acceleration may require an additional Coriolis term. Unlike velocity, acceleration requires this additional term to correctly connect the two reference frames. Understanding where this extra term comes from is essential when working with rotating reference frames. We now focus on the Coriolis acceleration. The Coriolis term is given by gamma sub c equals 2 omega cross v sub r. This equation tells us that the Coriolis acceleration appears when two conditions are present. First, the reference frame must be rotating, meaning that omega is not equal to 0. Second, the object must have a non-zero relative velocity inside that rotating frame, meaning that v sub r is not equal to 0. If either of these conditions is absent, the Coriolis term vanishes. Physically, the Coriolis acceleration is therefore a consequence of observing motion from a rotating reference frame. It is not an additional physical force acting independently on the object. Rather, it appears because of the way motion is described in the rotating frame. We can now use these principles to identify which terms remain under different types of reference frame motion. The first case is pure translation, where omega equals 0. Since there is no rotation, the rotational contribution disappears, and the Coriolis acceleration is also 0. In the second case, the frame undergoes uniform rectilinear translation. The entrainment velocity is constant, while the entrainment acceleration is 0. In the third case, we consider pure rotation, where the origins O and O' coincide. In this situation, the entrainment velocity is determined by v sub e equals omega cross O prime m. The acceleration contains rotational derivatives as well as the Coriolis term, 2 omega cross v sub r. This provides a practical diagnostic tool. Before performing calculations, we can identify the type of motion of the reference frame and immediately determine which terms should be included or eliminated. Let us now apply the composition laws to a concrete mathematical example. In the absolute reference frame R, the position of the point is given by x equals 2t squared, y equals 4t squared minus 4t, and z equals 0. Differentiating the position with respect to time gives the absolute velocity, v equals 4ti plus 8t minus 4j. Differentiating once more gives the absolute acceleration, gamma equals 4i plus 8j. Now consider the relative reference frame R prime. In this frame, the position is x prime equals 2t squared, y prime equals 4t squared, and z prime equals 0. Therefore, the relative velocity is v prime equals 4ti prime plus 8tj prime. The relative acceleration is gamma prime equals 4i prime plus 8j prime. Since the unit vectors are aligned, we can directly compare the quantities in the two reference frames. The objective is now to determine the entrainment motion of R prime relative to R using the composition laws. We can now determine the motion of the moving reference frame R prime relative to the fixed frame R. We begin with the velocity composition law, v sub e equals v absolute minus v relative. Substituting the two velocity vectors gives v sub e equals the quantity 4ti plus 8t minus 4j, minus the quantity 4ti plus 8tj. The x components cancel, leaving v sub e equals minus 4j. Therefore, the entrainment velocity is constant and directed along the negative OY direction. Now we examine the acceleration. Gamma sub e equals gamma absolute minus gamma relative. Substituting the two acceleration vectors gives gamma sub e equals the quantity 4i plus 8j, minus the quantity 4i plus 8j. The result is zero. Thus, the entrainment acceleration is zero, while the entrainment velocity is constant. We can therefore conclude that the motion of r' relative to r is uniform translational motion along the OY axis, with a constant speed of 4 meters per second. This final result illustrates the main idea of relative kinematics. The same physical motion can have different mathematical descriptions depending on the observer and the reference frame. That's all for today. See you next lesson.